For today's talk, so for today's talk, we will focus on the nanocellulose as one of the advanced and green nanomaterial that currently have attracts more interest in several industry applications. So for today's talk, it will cover from the basics of the nanocellulose, what the definition of nanocellulose, why we can consider the material as a nanocellulose, and I will touch some part on the synthesis part, and the surface modification, how we can tolerate the properties of nanocellulose that it can make some specific applications, and we will talk generally on the application of the nanocellulose. For that, I will give some example on the current study carried out on the nanocellulose to make a better understanding on the how the function of nanocellulose in the specific applications. Okay. So the definition of nanocellulose. So before we talk about nanocellulose, so let me give the introduction about its mother, which is cellulose. Okay, so cellulose is one of the of compound that consists of more than 1,000 or 100 of carbon, hydrogen, and oxygens, and is one of the compound minor compound of the carbohydrate. Okay, so carbohydrate can be classified by a number of sugar units. So the sugar unit, which is we call glucose, is the monomer, or is the smallest unit of the cellulose. Okay, so cellulose, they have, as mentioned, is the glucose. It have more than 3,000 units of glucose, and it's the most abundant organic compound on the earth. So it can be found not only in the plant, so because it's a one part of that support the rigidity of the plant. It also can be found in the bacteria material or microorganisms. So it has been in the 30% of the vegetables, 90% of cottons, and more than half from the wood. So cellulose basically cannot be digested in our body, but we need it as human. We need a cellulose as a fiber for our dietary. So as I highlighted, that cellulose can come from the bacteria and also plants. So what makes difference between the bacteria and plant is based on their purity and the strength. And normally for the bacteria, the cellulose that produced by bacteria, they are using for the food processing as the viscosity enhancers or thickening agents, because it's highly pure and it's highly strength because of the fibrous structure of it, and it can increase the water holding ability, whereby the cellulose produced by plant is normally it have the high strength because it becomes more rigid because of the interhydrogen bond between the cellulose polymer change. They make it more rigid, and it no taste and odorless and hydrophilic with the contact angle of 20 to 80 degrees. Okay, so it's highly hydrophilic due to the hydroxyl group, the abundant number of the hydroxyl group in its glucose glucose units, and it's considered biodegradable, and that's why it can be used in the most of the papers or tissue industries. So this is the structure, the general structures of the cellulose, which is composed of the glucose unit, and it have it has been linked. The glucose unit have been linked with the 1,4 glycosidic linkage that make it rigid, and also the hydrogen bonds that form between the hydroxyl group of the cellulose change that contribute to the rigidity and the crystallinity of the cellulose structures. So the cellulose, as I mentioned, is come from the bacteria and also the plant. So it can be extracted by the simple hydrolysis process, which is we are using the high concentrate of the acid at a certain high temperature at a certain duration of the reactions, and also a craft cooking, which is we're using the hydroxyl base group, which is the base at the basic pH, whereby the lignin content and the hemicellulose contents of the cellulose cellulose has been removed during the craft cooking process, And we are continuing with the bleaching, whereby we want to increase the purification of cellulose. Cellulose itself is the white color. So in nature is the white color. So that's why we have to remove the content of lignins that bind the cellulose in the microfibril form.
Dr. Laili,
Yes.
sorry to interrupt. Can you enlarge your slide?
Oh, it's not enlarged yet?
Yes.
Okay, sorry.
Thank you, Dr. Laili.
Okay, is it better?
Yes, better now.
Okay, so talking about the cellulose market trends, we say that as mentioned, it can be formed in the natural fiber and the chemical fiber. In terms of the chemical fiber, can be in the polyester, acrylic, or nylon. And in the natural fiber, it can be in the cotton and wood. So there are some interest on the application of the cellulose in the different market view. For example, it not only limit to the pulp and paper that previously, or the textile that previously has been used, but it also apply for the another high-end technology, for example, in the biotechnology, biomedicals, and also in the food industry, advanced food industry, because it is nature properties of the biodegradable, and also it's the low cost productions. So it's about it's about cellulose. Now we're talking about the nanocellulose, the nano size unit of the cellulose. So how the nanocellulose can be produced from the cellulose is due to the removal of the amorphous structures of the cellulose. So nanocellulose is a light solid substance that normally come from the plant, which is have a nano size in the cellulose fibers. And this nanosize can be achieved, as mentioned, they maintain the crystalline structures of the cellulose by removing some degree amount of the amorphous structures. And this is material in plastics, and they have the specific properties. Fluids generally is a thick because of the crystalline structure itself, and it have particle size in range 5 to 20 nanometers. Okay, so this is the figure shows uh, how the physical look of the nanocellulose. So it's transparent. So that's why it can be applied in the various application because it's colorless. So it will not give any impact on the appearance of the final products. So this is show how the nanocellulose produced from the cellulose. So cellulose, as I mentioned, is normally exists in the cell wall of the plant. Okay, so by removing the cell wall, we can get the microfibril, and the microfibril we can get the cellulose change. Okay, from the cellulose change, so we will do some acid hydrolysis process or the mechanical process that can produce two type of the nanocellulose, whereby it's either nanofiber cellulose or nanocrystal cellulose. It depends on the final structures of the cellulose itself. Is in terms of the fibrillars, normally it will form by the mechanical properties or the homogenization process with the semi-chemical process of the acid. But if you want to produce a nanocrystal cellulose, which is the cellulose with a high content of the crystal structures and the root needle shapes of the cellulose, so we will go for the acid hydrolysis process. In here, normally hydrolysis in the acid hydrolysis, the hydrochloric and bromic acid are much more preferred. Okay, and for the same thing with the bacterial cellulose, which is the source is from the bacteria. It also can produce the nanocrystal cellulose by the acid hydrolysis process. Okay, and followed by the centrifuge process, which is we can purify further the structure of nanocellulose. So talking about the properties, how interest these materials, because it comes from the natural source. So it considered a light. The density is low. It have a low density. What with the strong super uh, uh, high tensile strength, and it can be used as the absorbent. Electric. Basically, nanocellulose is non-conductive, but due to the some modification of on the surface or by the physical introductions of the conductive element, it can be a electrical conductive materials, and much probably is non-toxic. So we obtain some green materials for the applications, for the excellent applications. So then nanocellulose is the better, is a good choice. Okay, so this is the comparable properties of the nanocellulose as mentioned from the different source. So we have the different source here from cotton and wood, and we can say that the cellulose or nanocellulose from the wood products is higher in the tensile strength and the aspect ratio as compared to the non-wood materials. So if we compare with the nanocellulose with the Kevlar of the synthetic fiber, such as the Kevlar or glass fiber or carbon fiber, so we can see the crystalline cellulose have is a comparable density with this type of synthetic fibers. And if we compare with the tensile strength, it look like that the crystalline nanocellulose have half than the synthetic fiber, just as Kevlar, glass fiber, and carbon fiber. So but in terms of the elasticity, due to the removal of the amorphous structures, so crystalline cellulose normally have the lower elasticity properties as compared to these fibers. Okay, so this is the degree of polymerization, the relationship between degree of polymerization of the nanocellulose with the crystalline size.
Together. Its gravity keeps everything in orbit.
Is it the sound from me?
Jupiter, the tiny pieces of
Mr. Amara, can you mute your mic?
Away from the sun. Distances in our solar system is usually
Dr. Chi?
Yeah.
Okay. Okay.
Yep.
So okay. Okay, so this is the nanocrystalline hydrolysis process of the nanocellulose with the sulfuric acid at the different concentrations. So it can conclude that the high concentration of the sulfuric acid will produce a nanocellulose with the high crystalline size and the high degree of polymerization. And the same thing with the when we compare the tensile strength and the modulus of the nanocellulose as compared to the natural fiber or the petroleum-derived polymer, it can show that the nanocellulose has the high strength, but with the low modulus as compared to these other materials. So but as I mentioned to you that the nanocellulose itself is the hydrophilic property. So this is show how the amorphous structures of the nanocellulose have been of the cellulose have been removed to obtain the nanocellulose. But we have a big problem of the nanocellulose or cellulose to be used in the for example, in the polymer composite, because the hydrophilic properties of the cellulose fibers, and we make incompatible with the hydrophobic nature of the most of the polymer matrix or resins. So to overcome here, they have some recent study that have been carried out to do the surface modification of the nanocellulose in order to make sure that it have a compatible enough with the resin or with the polymer matrix. So there are several studies that have do the modification can be done during the synthesis process itself or after the synthesis process. So for example, during the synthesis process, we can use the sulfuric acid or hydrophobic acid or the prophonic acid to introduce the sulfonated group and the phosphoric group during the acid hydrolysis process. For the hydrolysis process with the chloric and bromic acid, normally only produce the hydroxyl group on the surface structure of the nanocellulose. Other than that, we can do the modification after the hydrolysis process, whereby we can introduce the tempo or the oxidation group on the surface of the nanocellulose. So this is the application of the cellulose. So it has the same application with the cellulose as well. It can be used as a textile, for example, in the pulp and the paper industry, whereby it can use as the to strengthen the paper and the paper tissue and so on. In biomedicals, it can use by the cancer therapy, biomakers, drug delivery for the food agriculture. So it can be used in the food packaging for the functional nanocomposite to enhance the viscosity or the thickening of the food materials. In the electronic, even though it's not conductive, but due to the addition of the conductive material or the surface modified with the conductive material, so it can have the height, it can be used as the height sensitive sensor, the chemical sensor or gas sensors. In the environment, so nanocellulose have been proved to be a good absorbent for the wastewater treatment, for the self-cleaning textile, and also as the catalyst support for the environmental catalyst. So as we can see the market, how the market trend of the nanocellulose or the how the requirement of nanocellulose in the market, so it increased simultaneously amount every year is almost double the value, increase almost double for the requirement of the nanocellulose. And normally people are require the nanocellulose in form of fibers have a better market value compared to the crystalline and the bacterial form. Okay, so major player of normally for the nanocellulose, they use for to so they use cellulose as the raw material for the chemicals, adhesive, and also the end use of the materials. So it can be applied for further on the pharmaceuticals and the biomedical companies. So we go for the second part on the nano biocomposite. What's the meaning of the composite itself? Is the combination of two different materials which have the two different properties in order to enhance the properties of the end of to enhance the uh, and final products. Okay, so for the biocomposite is normally a combination of the plant fiber with the resins to create the nature composite materials. So why the nanobiocomposite is important here is for the sustainable material, and it be used for the traditional natural fiber, agroforestry residue, industrial product, and the recycled fibers. And what is the nano composite? Or the nano, when we mention about the nano, so it's about the size. So why we need a low size in order to form a better composite? Because the low particle size with the low surface, we have the high surface area, which means that the interaction of the composite interaction of the fillers or particles with the matrix is higher as compared to the one with the higher particle size. So the application can be the polymer nanocomposite due to this enhanced properties as compared to the one in the micro size. So it can be used in the environment, for example, for the environment application, energy storage, sensing, and the novel catalyst. Okay, so for the last part is for the nanocellular biocomposite in the industry applications. So combination of the nanobiocomposite, which is the product from the natural source, and then at the low particle size, which is the nanocomposite, will have a good, we show the excellent properties as the reinforcement agent, as the in terms of the solubility, conductivity, biodegradability, and absorption properties, which is we will cover here, and I will provide some example of study to make and to gain the understanding about how the function of the nanocellulose for these respective properties. As the reinforcement agent, as I mentioned, is we compare on the in terms of the mechanical properties of nanocellulose itself, it have, even though at the low density, which is at normally is at the low density, but it have a high tensile strength. It normally is a double than the carbon fibers and the glass fibers. and is 10 times higher than the aluminum and the steels. So that's why it can be used to increase the strength of the materials, and it can be used further as for the constructions, for the high quality paper, food packaging, membrane for wastewater treatments, height resistant coating, and height stable form. The small particle size of nanocellulose itself also help for the force distribution, the homogeneous force distribution between the resin and the particles. So it will make the it will make the end product become more resistant and more stiff as compared to the material with no reinforcement agents. So this is the example from our study that we use a nanocellulose that we have modified with the antioxidants for the nitrile glove industry. So here we produce a multifunctional nanocellulose as the green additive. And the reinforcement effect of this nanocellulose is expected from the crystal structures of the nanocellulose itself, the particle size, the nano in the nano size, which is it can induce the height surface area, and also due to the hydrophobic interface of the nanocellulose after the modification with the acetyl compound, which is produced the acetyl nanocellulose. So these three factor will provide a good reinforcement agent towards the glove materials. And also due to the natural source, so this material can be biodegradable, and also and the introduction of the introduction of the antioxidants, which have the phenolic group, can have a free radical stability stabilities uh, and also the thermal stability towards due to the crystal structures. So what the result obtained that the addition of the nanocellulose at the certain pHr or the certain volume up to 3 to 4 pHr can increase the tensile strength for 40 to 30%. And as be expected, since we are using the nanocrystal, it's not the nanofibers, so the elastic modulus is reduced slightly from the native from the native uh, from the native NBR glove. So if we're talking about the hydrophobic, okay, so due to the addition of the acetyl group, so we have managed to change the hydrophilic properties of the nanocellulose brought by the hydroxy group to and make it more compatible with the NBR matrix, which is hydrophobic in nature. So this is the other studies whereby they introduce the nanocellulose as a reinforcement agent of the PVA or polyvinyl acetate. Okay, PVA itself is hydrophilic, so there's no need for them to change the surface of the nanocellulose, and that's why the nanocellulose here is only produced have been produced by the HBr, which is at the end produce the nanocellulose with the abundance of the hydroxy groups. So a good interaction of the nanocellulose with the PVA, which is both of them are hydrophilic, then that why they increase the tensile strength of the material itself. So this is the comparison. So they do the synthesis process at the different the hydrolysis process at the different concentration of the HBr, and it shows that the HBr at the high concentrations produce the high strengths of PVA composite as compared to those in the lower concentrations. So this is another studies whereby they produce a nanocellulose with the sulfuric acid to have the sulfonated nanocellulose, and they do the comparison between the sulfonated nanocellulose with the hydrochloric nanocellulose, which is the nanocellulose with the hydroxyl group, the one with the hydrophobic, which is the sulfonated, and the hydrochloric, which is the hydrophilic, and it shows and they both of them has been introduced to the xylants, and it showed that 50% of, and it showed the improvement of the nanocellulose, hydrophilic nanocellulose, which is produced from the hydrochloric acid, is higher as compared to the is lower as compared to the one with the sulfonated nanocellulose. This is due to the interhydrogen bond and the high aspect ratio that brought by the sulfonated nanocrystal cellulose. So this is another study whereby they are try to produce to introduce nanocellulose, okay, with the hydrophobic PE, polyethylene. So due to the hydrophobic properties of the PE, so it will not give a good interactions with the hydrophilic structure of nanocellulose. So what they do is they introduce the PVA as the bridge or linker between these two groups, and it shows that the properties, or especially the mechanical properties, improve simultaneously due to due to this process. And another one, they have used the how the structures of the nanocellulose have been effects at the end of the properties of the composite. And this study, they are used the acrylic latex. Okay, so due to, and it shows that the nanocellulose in form of nanoball have give a better interaction with the acrylic latex as compared to the one in form of the viscous. So why the nanocellulose is most interesting, not only on in terms of the mechanical property itself, but due to the biodegradability properties. So here, that's why nanocellulose have a wide application on the for the product that need it to be biodegradable. For example, it can be used for the environmental friendly plastic, biodegradable rubber materials, for cosmetic, pharmaceutical, food industries, and so on. And how nanocellulose act as the biodegradable agents, because nanocellulose, they have the cellulose structures, and the cellulose structure, they have a carbon compound which it can be consumed by the microorganism, for example the bacteria, fungi, or algae, and it will enter the biocycle, and it will be degrade or it will be disintegrated polymer functions of biomass, water, and carbon dioxide. Okay, and the biodegradability factors of the biodegradability properties of the nanocellulose composite depend on the several factors. For example, in terms of duration, how long we introduce the material or the composite in the degradation media. Okay, the polymeric fractionation mechanism, the waste residue, and the filamentary interactions, whereby the composite with a strong filler to matrix interactions tend to have the lower biodegradability properties as compared to the one with the uh, with the uh, weak interactions. Okay, so this is the study we do for the continuity between after the NBR acetylate NBR antioxidants for the NBR composite, and it shows that after the 6 months, 50% of the glove or 50% of the matrix rubber has been degraded. And this is another one where they introduced the nanocellulose in the natural latex and the cross-linked natural latex. It showed that due to the cross-linked structures, so the degradation of the nanocellulose become more harder, and it's and due to the cross-link structure and the strong interconnects, so it will make the cross-link nanocellulose is more resistant towards the biodegradations as compared to the one with the natural latex, which only have a physical interactions between the natural latex and the nanocellulose filler. So this is the how the crystallinity effects on the degradations of the composite. And for that, they have studied on the thermal degradation, and it shows that the high crystalline material has a possibility for lower degradation as compared to the one with the low crystallinity structures. Okay, and as I mentioned, the nanocellulose are the potential material for the electric and electronic conductive material in terms of the energy, for example, in the sensor, for the battery, lithiums, corrosion protection, conductive coating, and so on. But the limitation of the nanocellulose in this aspect is because it's not conductive. So that's why we need to introduce the conductive material, for example, through the blending, coating, or doping process to make sure that the conductive material or the conductive particle have been introduced. Okay, so what made the nanocellulose interesting for the conductivity properties because it's the mechanical stable. It have the smooth surface, transparent, which is we didn't alter the final properties of the materials, and it have a possibility on the high possibility for the surface modifications. So it can be, we can do the manipulation of ions, electron, and photon, and much probably in the term of the production cost is cheaper than glass or carbon fibers. So this is the example of studies that whereby they uh, introduce or they incorporate the nanocellulose in terms of fibers. Why we need fibers for the elastic modulus, okay, and with the graphene, okay. So this is for the moving sensor applications, and it shows that highly stretchable graphene nanocomposite paper it has been produced with the high strength, okay, and stretchable graphene nanoparticle. This stretchable graphene nanopaper is efficient for the human motion detection application because it can detect at the small motions, uh, and have up to 100% of strength. So polypyrrole, one of the material that normally used for the conductive material, for the freestanding material for the energy storage applications, and it shows that the surface modification of the nanocellulose with the polypyrrole can produce a good coating materials and have the charge capacity increase as compared to the native polypyrrole. It's not only the nanocrystal cellulose have the good interest for the conductive material, but also for the bacterial nanocellulose. For example, this study carried out between bacterial nanocellulose, so they use as the conductive material by combining the bacterial nanocellulose with the CNT, carbon nanotube, and it have a combination of these two materials have the strong interactions due to the van der Waals and interhydrogen bonds. And that's why the final product, they have a consistent symmetry charge-discharge curve. And it have a good potential for the energy storage devices. And as mentioned, how the nanocellulose, the cellulose itself can, or nanocellulose can be porous materials. So, and due to the porosity, so it can be used more on the wastewater treatment. So the porosity of nanocellulose normally when it in the form of the fibers and not in the crystal form. Okay, so it can be used in the wastewater treatment, in the for the thermal insulate material, in the food packaging, aerogel, and as the protein absorber. So nanocellulose composite as absorbent, why it are a good candidate for to be used as the absorbent because of the hydroxyl group itself. They have abundant of the hydroxyl group, which is can be further functionalized easily with the other material, whereby by the hydrophobic or the hydrophilic materials. And it also have the high hydrogen barrier properties. It can be direct embolized onto the different substrate, of course, due to the particle size, the low particle size, so it have the high surface area as respect to the aspect ratio. and of course for the mechanical properties and easy to be reused or recycling purpose. So this is important for the material, for example, for the absorbent in the waste material, that currently we're looking for the material that can absorbent that can be recycled in term to for to reduce the production cost of the absorbent. So this is example whereby the nanocellulose as the absorbent have been used with the combination of the alginate. Okay, and as you know, the alginate itself is have the weak mechanical, uncontrolled absorbance, and degradability. So the combination of the here the nanocellulose first has been modified with the tempo oxidations. The oxidized group have been introduced to the nanocellulose to make sure that they have a good interactions and homogeneity with the alginate, and they're followed by the production of sponge that have the high strength, porosity, water absorption, and structure stability. Okay, and it shows that the tempo nanocellulose coupling with the alginate provide a rigid nano reinforcement effects that have overcome the issues of the natural alginate as the absorbent material. And the next study also they done with the nanocellulose with the glycerol sodium calcinate composite, and this is for the food packaging applications in order to increase the water vapor permeability of the glycerol sodium calcinate itself. And it shows that the moisture barrier have been improved by the nanocellulose, and the present part of the crystalline part that present in the nanocrystalline cellulose increase have been slow the diffusion process of the moisture for the glycerol sodium calcinate composite. Nanocellulose for the have been also introduced for the collagen, and here we are using the nanocellulose in the fiber form. And nanocellulose have been modified first with the aldehyde before it can be directly introduced to the collagens. And it shows that the introduction of the nanocellulose increase the water absorption of the this scaffold, which is the collagen scaffold, in the hemostatic and the wood tracing applications. So instead of various application or potential application of the nanocellulose, so they have still exist the challenge of the nanocellulose that can be that need to be overcome. The first one in the surface modifications, as I mentioned, that nanocellulose itself, it have only abundant group of the hydroxyl group, and it considered hydrophilic, whereby most of the material or resins that available in market is the hydrophobic. So how we can capture this limitation is by do the surface modification of the hydroxyl group on the polymer change of the cellulose, and to make it by introductions of the hydrophobic compound, or we can do it during the synthesis process of the of the nanocellulose during the acid hydrolysis process by using the sulfuric or a certain type of the acid. Okay, and that's why the surface can be engineered to achieve a good dispersion and bonding to the matrix. So the next limitations of our nanocellulose to be used in the industry on the due to the structural stability. Okay, so as I mentioned that even though the nanocellulose is from the cellulose, which is we can consider is biodegradable, but due to the some changes on the properties of the cellulose to produce a nanocellulose, for example, in terms of the amorphosity or the amorphicity and crystallinity, in terms of the particle size, molecule weight, and so on. So they have different structures as compared to the cellulose. So that's why sometimes nanocellulose is high sensitive to the UV exposures, especially for the intense sunlight, wet and humid conditions, and also the chemical exposure as compared to the cellulose itself. So the next limitation that I would like to highlight on the application of nanocellulose further in different industry application is on the scale up productions. So as I mentioned that the nanocellulose can be produced by the even for the physical or by the semi-physical or by the chemical approach. Okay, for the physical approach, normally we are using the homogenizers, and it consume the high energy and high energy and a high cost product to produce nano NCF nanocrystalline nanofiber cellulose. Okay, for the acid or hydrolysis process or hydrolysis process to produce a nanocrystalline cellulose, normally we have some issues about the remaining acidic material and how we can neutralize the produced nanocellulose. So the last challenge on the source of the nanocellulose normally is from the lignocellulosic biomaterials, and that's why we have inconsistent or inhomogeneous properties that will produce by a different lignocellulosic source materials. So I have several publication on the nanocellulose. So this is some my publication on the nanocellulose from the synthesis until the application of the nanocellulose. And for the further details, you may directly contact me through this email address. Thank you.
Thank you, Dr. Laili, for your wonderful presentation. I shall open to the floor if you have questions to Dr. Laili.
Hello.
Hi.
Yeah,
Hi.
Amara here.
Hi, Amara.
Yeah,
How are you?
my question, fine. I have a question with respect to nanotechnology and that of the material being used in terms of mono and
Yes.
heterogeneity, because we're looking at sort of a biocompositions, okay, of two different material. But it is compulsory that you have to use two different material in order to get a solidified nanomaterial instead of nanotechnology to be more, more vibrant, or you need more materials in terms of degradability. Because I believe that if it is only two materials, sort of biocomposite, okay, that is used, I'm not quite sure that it may be much more, let's just say, heightened or much more reliable compared to more material to be used. So from your analysis, it is only two materials that may be needed in order for you to get a sort of concrete result in terms of biodegradable or biomaterial, such as glove and stuff and things like that we could use.
Okay. Okay. Talking about the bacteria nanocellulose, so it can be produced by the acid hydrolysis groups. Okay, and a good thing about the bacteria nanocellulose as compared to the other type of the nanocrystalline cellulose is due to its biocompatibility. And normally the bacteria nanocellulose, they will produce in the product is in the positive charge. In the positive charge, so that's why it will be good for the degradations and so on. Okay, to answer your question about the combination of bacteria to produce biocomposites, is it your question, Amara?
Yeah.
Yeah, the two type of the bacteria that is suggested to produce a biocomposite with the better homogeneity and compatibility. So normally for the bacteria is it is depend on the, it's not only depend on the number of bacteria or on the source of the bacteria, but it's also depend on the particle size of the aspect ratios of the nanocellulose that produce from the from this hydrolysis process. Okay, so and the particles, the nanocellulose with the lower high aspect ratio with the lower particle size normally can give the composite with the high strength composite as compared to the ones in the high surface area and the low aspect ratios. So it depends, and also the second factors that can contribute to the production of a good nanobacteria, NCF or NBF or nano fiber bacteria is on the concentration of the acid used and the duration of the hydrolysis process. So high concentration of acids normally will produce a form of the nanocrystal as compared to the nanofibers. So we have to play around with these parameters. It's not only the source of the bacteria, but it's also the parameters during the production process.
Thank you.
Okay.
Thank you, Doctor.
Okay, thank you, Amara, for the questions. Are you working on the nanocellulose?
I kind of having some things to do with it a little bit.
Yeah, it's a good it's a good potential materials with various applications. So maybe you can consider it. So
Thank
if
you.
I can know, may I know what kind of material you're working with now?
We do try to use a material within the soil, from soil,
Okay.
from the soil to see whether we can able to create an issue that has to do with agricultural development and has to also do with a material that may be used like fibers in the long run. So there are other different hydrolysis processes I think we are undergoing to ascertain some materials as well as research ongoing.
Okay.
Yeah.
So is the application on the drug delivery?
Yes.
Okay.
Yeah. Thank you.
Thank you, Amara.
Laili, just now you mentioned there are two major different types of nanocellulose. One is nanocellulose fiber. Another one is crystalline cellulose. And based on your opinion, which one is more suitable for a conversion from a nanocellulose into some wearable chemicals, some small molecule wearable chemical? Shall I use fiber or the crystalline type of nanocellulose?
Okay, Dr. Ki, thank you for the question. So your intention is you want to do the further surface modification of this material. Which one is much more preferable, which is in form of the fiber or in form of the crystal?
No. My question is not on the surface modification. I want to digest into a smaller molecules.
Okay. Okay, so you want to okay, so what is this? Okay, Dr. K, is these two materials, which is fiber and crystal. So what the difference between these two is due to the surface area and the aspect ratio. Okay, so for the fiber, it have the higher aspect ratios because of the length and the low diameter of the structures. But for the crystal, so it have a lower length, but with the bigger diameter. So that's why it have a higher aspect ratios. So if you want to cut or you want to cut it into the structure into the smaller pieces, so it's depend on your application. So for example, if you're looking for the hydroxyl groups, they have the hydroxyl groups on the surface. So if if you are looking your application is to use the functional group on the surface of the hydroxyl group, so crystal is much more preferable. But if you're looking for the CO group, which is the glycosidic linkage has been cut in the glucose ring, so CNF is much more better. So it's because they have a different morphology of these two. So I'm not sure if your question, whether you want to make it in a smaller, small, because you want to make it in a smaller particle. So which part you are interested, on the surface or on the interfacial, on the beta glycosidic linkage of the nanocellulose?
Thank you, Dr. Alaili. I get your answer.
So
Is there any more question to Dr. Alaili?
I think we approach to the end.
Yeah.
5 minutes more. 5 minutes more.
Alternatively, you may also raise your question through email to Dr. Alaili.
Or if you can use the chat room here.
From the chat room, there is one question from Amara. He's asking whether your slide is available for his future research and review.
Yes, but in the PDF format.
PDF format.
Yeah, I will provide in the PDF format. I will provide to the organizer the slide. Actually, it's not a research slide because most of the example I use here is from the year of. So most of the example I'm using here is from the not in the recent year. So I will update some data in this slide first before do the sharing with the organizer.
Sure.
Sorry, the background sounds.
No worry. Yeah. So if we have no more questions, shall we once again thank Dr. Alaili for her wonderful presentation and sharing with us about nanocellulose. We see a lot of good potential about nanocellulose. Please join me to thank Dr. Alaili for her presentation today.
Thank you very much, Doctor, for the presentations. Hope to catch up again for the future in terms of future presentation as well with you. Thank you.
Okay, thank you for your time. Thank you for to come, and I wish everyone to stay safe, stay healthy, and good luck for all of us.
Yep.
Thank you.
Stay safe, everyone. Yeah.
Assalamualaikum.
Bye-bye.
Bye.